Good day everyone, I'm Norman Wildberger and we're talking about box arithmetic and applying it to number theory, particularly the Euler product formula for the zeta function and sort of associated things. And for us, the central sort of object here is actually what we call the fundamental identity of arithmetic, which is an identity involving boxes and the caret operation. And we've sort of shown how to take that identity and use it to cook up variants of the Euler product. I want to go further here by talking a little more about multiplicative functions and then applying them to this situation. And perhaps in the next video, we'll bring in Dirichlet series into the story also. So we're touching base with some pretty fundamental and important ideas from number theory, but perhaps in a somewhat novel combinatorial way. Okay, so the fundamental identity of arithmetic is this one here. Here is the box of powers of 2, then powers of 3, then powers of 5, carrying on over primes. We're taking the caret of all these boxes, and over on the right-hand side, we have the box consisting of all the natural numbers. And what we saw last time is that if you take an integer n, then well, you can raise everything to the nth power and you still are going to get an identity involving boxes and their carets. So here we've just taken all of these and raised them to the nth power, raised all of these to the nth power, and so on. And on the right hand side, raised the natural numbers to the nth power. And then we saw that to connect with the Euler product, what we do is we apply this sum operator, which takes one of these boxes and adds up all the elements in the box. So the sum of all these elements, then times the sum of all these elements, times the sum of all these elements, etc. Okay, that should in some sense be equal to the sum of all of these. Now, when n is a natural number, like 5, well, it appears that none of these things make at least immediate sense. But if n is a negative number, like -5, well then, these sums here, according to a classical analyst, they converge. Now, they don't actually converge to me because I'm not allowing infinite arithmetical processes. But nevertheless, the standard story is that if you took n to be, say, -8, okay, then you would get actually a legitimate identity, and that's essentially the Euler product. So the crucial thing here is the multiplicative aspect of this taking powers operation. So we want to exploit that and investigate multiplicative functions more generally, so we can cook up variants to this important example. So what made the previous example work is the multiplicative property of taking a power, that a times b to the n is equal to a to the n times b to the n, for actually general natural numbers a and b. So this motivates us to define the following: a strongly multiplicative function from the natural numbers to the natural numbers, or perhaps from the natural numbers to the integers, is a function that satisfies this basic property, that f of a times b equals f of a times f of b. So for example, raising a number to the nth power is an example of a strongly multiplicative function. Now, somewhat weaker than that is just the notion of a multiplicative function. Okay, so it's the same story. We have the same condition that f of a times b equals f of a times f of b, but now we require only that it works when the numbers a and b are relatively prime natural numbers. In other words, when they don't have any common factors. Notice that their GCD, or greatest common divisor, is 1. All right, so this is a weaker condition. That means there's going to be more of these multiplicative functions than there are strongly multiplicative functions. It will turn out that just multiplicative functions are enough for us to make this story work. And it's pleasant because there's actually quite a lot of really interesting multiplicative functions that play an important role in number theory, even in classical number theory. Okay, so let's talk about some important multiplicative functions. One of them is the Mobius function, which is very simple. So a natural number is sent to either 1 or -1 or 0. It's sent to 0 if it has a squared prime factor in it. In other words, if one of the primes in its prime decomposition appears with an exponent greater than 1. So for example, 12 has 2 squared as a factor, and so mu of 12 will be 0. So if the thing does not have any squared prime factors, so that means that all the primes that do appear in the expansion of this, this number into prime factors, if all of them are distinct, okay, then mu of that n is 1 if there's an even number of such prime factors, and it's minus 1 if there are an odd number of prime factors. Okay, so it's not too hard to see that this is a multiplicative function, and it plays a big role in number theory. It's not actually going to be so important for us for what we're doing today, but it will figure importantly when we start talking about Dirichlet series in a lecture or so. Okay, another one, the Euler-Tauschent function, phi of n. This is the number of natural numbers k less than n, which are relatively prime to n. In other words, which don't have any common factor with n. So for example, phi of 7 is 6, because all the numbers 1, 2, 3, 4, 5, and 6, all the natural numbers less than 7 are relatively prime to 7, because 7 is a prime. Phi of 8, on the other hand, well, the numbers which are less than 8 and relatively prime to it are 1, 3, 5, and 7, and there's 4 of them, so phi of 8 equals 4. So the basic rule is that if p is a prime, then phi of p equals p minus 1, and phi of a power, phi of p to the k, equals p to the k minus 1 times p minus 1. And you can think about this in the following way. This is the same as p to the k, okay, which is all the numbers from 1 to p to the k, minus p to the k minus 1, which are all the multiples of p. All the multiples of p, which are less than or equal to p to the k, are p times 1, p times 2, p times 3, etc., all the way up to p times p to the k minus 1. So there's p to the k minus 1 of them. So we have to take them away. All the others are relatively prime to p to the k. So this is an example of the thing where we see that's not strongly multiplicative, because this thing here is not the kth power of this. Okay, so it's not strongly multiplicative, but it is multiplicative in the sense that this formula here suffices to allow you to calculate phi of any number, because you just decompose this number into prime factors, assuming you can do that, and then you apply these formulas to each one of those prime factor sort of powers. Okay, and the result will just be the product of all of those. Okay, so this is the Euler-Tauschent function. Okay, so it's going to be interesting for us now to apply this Euler-Tauschent function, phi, to our fundamental identity of arithmetic. So here's our fundamental identity of arithmetic, which you've all seen quite a lot now. I'm just expanding the natural numbers on the right-hand side a little bit, because it's going to be interesting to see the values of these various things. So what we're going to do is we're going to apply phi to each element here. Every natural number that you see here, we're going to apply phi to it. So phi of 1 is 1. Phi of 2 is 1, because that's a prime. 1 less than it is 1. Phi of 2 squared, well, that's 2. According to the formula, that would be 2 to the k minus 1 times 2 minus 1. So that's 2. 2 cubed, according to the formula, that's 2 squared times 2 minus 1. So that's 4. So actually we see that we're getting powers of 2 here also, but sort of staggered. Over here, phi of this is 1. Phi of 3 is p minus 1, or 2. Phi of 3 squared is 3 times 3 minus 1, so 3 times 2. Phi of 3 cubed is 3 squared times 3 minus 1, which is 9 times 2, or 18, etc. So again, we get another kind of geometric series, okay, but starting with 2, common ratio 3. And the next one, 5. Phi of 5 is 4. Phi of 5 squared will be 5 times 4, which is 20. 5 cubed, its phi is 5 squared times 4, so that's 100, and so on. And you keep on going. Okay? And on the right-hand side, well, the phi of all of these things is this thing here. list here. So phi of 1 is 1, phi of 2 is 1, phi of 3 is 2, phi of 4 is 2, phi of 5 is 4. That's the easiest one because it's a prime, so it's 1 less. Phi of 6 is 2. And if we didn't know that, well, phi of 6, the things which are relatively prime to 6 are just 1 and 5. Another way of getting that would be to take 2 and 3, which are relatively prime. Okay, phi of 2 is 1, phi of 3 is 2, therefore phi of 6 has to be 1 times 2. Phi of 7 is prime, 6. Phi of 8 we've already talked about, that's 4. Phi of 9, okay, that's same as 3 squared, we know that's 6. Phi of 10, that's the product of phi of 2 and phi of 5, so 1 times 4, so that's 4. 11 is a prime, so phi of it is 10. And phi of 12, that's the product of 3 and 4. 3 and 4 are relatively prime. So the product here is 2 times 2, we get 4. 13 would be 12, and so on. So now we're getting an identity of the carets of these various things. Right? So the statement is that, for example, 4s. The 4s that appear on the right-hand side, namely this one, and this one, and this one, are obtained by careting these boxes and seeing where you get 4s. So that amounts to how can you choose a box element here, a box element here, a box element here, and so on, so that the product of all of those is 4. 1 times 1 times 4, or there's an example. Or 1 times 1 times 4, that's another example. Or 4 times 1 times 1, that's another example. Or 2 times 2 times 1, so that's another example. And I guess maybe that's all there is. Okay, so that's cool. So we have an identity, and we could apply the sum operation, okay? But on the face of it, that's not perhaps immediately interesting because we sort of see that these sums appear like they're all going to be divergent. But what we can do is we can go back and do exactly the same kind of thing that we did to the zeta function story. We could take this identity and say apply an nth power. Okay? Still the same idea. We can apply the multiplicative function of raising something to the nth power, and we're still going to get an identity exactly of the same kind. But now we just have to take all of these elements and raise them all to the nth power. Okay, all of them. And that's going to be another identity of M sets or boxes. But now, if we judiciously choose n to be a negative of a natural number, then we can expect, at least classically, that these guys here, well, the entries are getting big. And so if you raise them to a negative natural number power, you're getting something which gets smaller and smaller. So there's a chance that this thing here will converge in some kind of traditional sense. Okay. And the same thing will apply to each one of these things here. We're going to get geometric series, in fact, okay, that we can write down formulas for them. And so we're going to get some kind of identity, very much like an Euler product for the zeta function. But now it's quite different, because instead of having the natural numbers down here, we have the totient values of the natural numbers. So let's see what kind of identity we get. And so now what we want to do is we want to write down formulas for the sums of the things that are in these boxes. So all of this is the first sum, and then we have to multiply by this next sum, and then this the next sum, etc. We multiply them all together, and we should get this sum on the right-hand side, at least in some sense. So on the left-hand side, we have a product over primes, okay? And what we have is we have 1, okay? Each one of them starts with 1. And then there's a geometric series, okay? Like this one here is a geometric series that starts with p minus 1 to the n. This is the p equals 5 case, so p minus 1 to the n. And then there's, it's just a geometric series built on that where the common ratio is 5 to the n, or p to the n in general. So 1 plus p to the n plus p to the 2n plus p to the 3n, etc. The geometric series. So we're taking the product over all primes. That's what's on the left-hand side of this. On the right-hand side, well, we're summing over the natural numbers k. We're taking phi of k. Those are these numbers, 1, 1, 2, 2, 4, 2, etc. And we're raising them all to the nth power. And as I mentioned, maybe we have a better chance of getting something that looks sort of familiar to us in a sort of convergent sense if we make n to be a negative integer. So maybe we set minus n equals m. Okay, we make this replacement. So this n is replaced with minus m, and then it ends up in the bottom here. So we get 1 over p minus 1 to the m. This is a geometric series. Right, so its sum will be 1 over 1 minus the common ratio, which is p to the n. But p to the n is the same as p to the minus m. So in the denominator here, we have p minus 1 to the m times 1 minus p to the minus m. We're taking the product of all of those overall primes. And over here, well, we just get the sum of the 5 k's, k running through all the natural numbers, now raised to the minus mth power. This is a kind of a cool formula, and if you've been following the lecture, you think, well, yeah, we're just applying phi to this fundamental identity. It's not a surprise. So if you've seen the derivation up till now, you say, yeah, it's not a surprise. But if I just sort of showed you this formula, showed you the Euler product formula for the zeta function, and I said, oh, here, by the way, is something that's a little bit like that, a little bit different, you might not immediately sort of twig that this is actually a relatively simple kind of consequence of essentially the same identity that underlies the zeta function story. Right? It looks different, even though it has the same general form, a product over primes and a sum over natural numbers. Okay, so here I've rewritten the formula so we can admire it. And we should ask, well, yeah, but is it really true? Is it in some sense true? Can we check it somehow? Well, yes, we can, because here we're taking products and here we're taking sums. And although these are ongoing, the idea is that if we choose some m, which is a natural number now, then we have some kind of convergence. That is, we are expecting that as we carry on, we're sort of approaching some general value. Maybe we're not approaching a real number, but we can just say that as we carry both of these computations on, we should expect that they start looking close to each other. So we can check that. Let's check it, say, with m equals 10. So we have a reasonably big power down here, so that these things go to 0 reasonably quickly, so that we have a better chance of convergence quickly. All right? And let's compute this thing here. All right, so this is the product of primes, p, up to 20. So 2, 3, 5, 7, 11, 13, 17, and 19. So I've taken those 8 products, all of this form. 1 plus 1 over p minus 1 to the 10, 1 minus p to the minus 10. Of course, I haven't done it. My computer has done it. And my computer tells me that this is approximately 2.002933573 ... Okay, approximately. Okay, and on the right-hand side, well, we could take the sum of 1 over 5k to the 10. Say we're k going from 1 to, say, 13. Basically the ones I showed you already. Well, my computer can calculate that also, and it gets 2.002933535. Hey, so that's not bad. We've got equality up to 7 decimal places. That gives us a fair amount of confidence that this is a reasonable formula. Okay, and there's something magical about it, because on the face of it, these things are very different, right? Here is some product over primes, and here is some sum over natural numbers, and we're taking this funny sort of phi, the Euler-Totient function, to some power. It's interesting. And now, has this been studied? Well, I don't know, actually. I haven't checked. My guess is probably number theorists know this. But maybe it's not well known, but maybe if you're a number theorist, you can tell me if this is well known or not. But in any case, I just want to suggest to you that this is sort of one of many kind of possible Euler-type formulas that we could cook up without really that much work, just by taking the fundamental identity of arithmetic and applying some convenient, in this case, sequence of multiplicative functions to all the entries. So what we did, right? We took the totient function and then we raised things to a power. So we actually performed two multiplicative functions on the elements of the identity. Okay, so we need more multiplicative functions. So here are some more very common and important multiplicative functions coming from number theory. And I just remind you, the multiplicative here means, it doesn't mean strongly multiplicative. So it means that when you apply one of these things to powers of a prime, you have to sort of have a separate formula for each power, okay? And that's enough for us to be able to apply the story to our fundamental identity. So the divisor count function, where d of n is just the number of divisors of natural number n. So for example, 6 has 1, 2, 3, 4. These are the divisors of 6. And the number in this set is 4. And here's what the function looks like. Numbers 1 through 20. So d of 1 is 1, d of 2 is 2, d of 3 is 2, d of 4 is 3, etc. You just have a look. Okay. Number of divisors of n. Another kind of related thing is the sum of the divisors function, sigma of n. So now this is the sum of the divisors of n. In summation notation, sigma of n is a summation over d dividing n of d. And a crucial property is that sigma of p to the k is 1 plus p squared plus all the way up to p to the k. And that's a geometric series. So the formula is p to the k plus 1 minus 1 over p minus 1. And of course, if you know this formula for a power of a prime, then you can pretty easily calculate sigma of n for n, a natural number, as long as you know the prime factorization of n. So that's another multiplicative function. And there's a variant to that, so somewhat more generally, we can also look at the sum of the kth powers of the divisors of n. So sigma sub k of n is the sum over all d dividing n of d to the k. So sum of powers of divisors. So when k is 0, well, then you're just counting them, okay, and then that's really this one here. And when k is 1, then you're just taking the ordinary sum, that's this one here. So this is some generalization of these other ones. These are all multiplicative functions, okay? So in principle, we can play the same game that we've just played with the totient function for any one of them. So in summary, there are lots of opportunities for cooking up Euler-type product formulas, with the general idea being that we start with the fundamental identity of arithmetic, namely this thing here, okay, consisting of boxes, one associated to each prime number on the left and the box of all natural numbers on the right. And then we apply various multiplicative functions to all the elements. And then after that, we sum up the elements by applying the S operator, which converts these boxes into sums, potentially numbers, and converts the carets into ordinary products. So we have a product of sums for all of these boxes equaling some sum over the natural numbers of whatever it is that we're looking at. So in this story, there's a helpful tip here, which is that the product of multiplicative functions is also multiplicative. So that means that you could iterate this story. Well, we've already done that once, right? We already applied the totient function and then we raised things to a power to try to get something that more easily converges. Well, we can do the same kind of thing here, but we could, in principle, iterate this a number of times and apply one multiplicative function and then another and then maybe another one. And we're going to get a whole bunch of identities. And these identities are, maybe they're interesting. They're telling us something about the world of numbers. In fact, this is not so far from what number theorists already do. This kind of story is not at all far from standard classical sort of analytic number theory. And that becomes even more into focus when we shift to Dirichlet series in my next talk. I want to show you that this box arithmetic point of view becomes particularly useful when we're analyzing convolution of arithmetic functions, Dirichlet convolutions, and Dirichlet series. Hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.